Hi guys, welcome back to chapter 13. We're going to cover sections B and C today and start talking about some specific simple machines, okay? So let's start talking about levers. You probably know of levers as seesaws, okay? If you've ever played on a seesaw in a playground, you've been making use of a lever, okay? Basically, a lever is a simple machine that consists of a rigid bar turning about a pivot point. And it's considered rotation, okay? So if my finger is the pivot point and this is the rigid bar, this bar wants to rotate around the pivot point, okay? Typically it's on the ground or there's something preventing it from going all the way, but this is considered a rotation, okay? The fulcrum is the actual pivot point. So in this situation, it would be my finger. It would be the center of the seesaw if you were on a seesaw. And it could be in different locations. We're going to talk about different types of levers, and the fulcrum moves in all kinds of different locations, okay? When we talk about these levers, we talk about something known as torque, and torque has to do with that rotational movement. You might have a torque wrench to work on a car, and that's actually rotating the bolts in your car. But torque can also apply to these seesaws, these levers, okay? So the force is trying to cause the object to move, but it's actually making it want to rotate all the way around that axis, okay? And then the moment arm is the distance between the force and the axis, okay? So let's look at this seesaw right here. Here is the pivot point. Let me get my pen. Here's the pivot point right there, okay? So the moment arm, the distance between this dude and the pivot would be that. This would be considered D input, distance of the input, okay, because he's putting the force in. And then this would be a much smaller one. This would be out, D out. That's an O, believe it or not, okay? And then the force of the object is taken into account when we want to compare these torques, okay? So we would talk about the force of the output object, and we would talk about the force of the input object, okay? We're really talking about weight, okay? So that dude's pushing down on the seesaw against gravity, and we've got this 1 ton weight that weighs a ton because gravity is acting on it like that, okay? The fact that this is lower tells us that the force times this distance is a higher number than this force times this distance. So we can adjust these things to make them equal. We'd have to move the fulcrum or increase the force in order to get that seesaw balanced, okay? So let's look at a couple of scenarios here. Here is a balanced one right here, okay? You've got 2 people, they have the same weight, they both weigh 50 newtons, their moment arm, their distance is 10 feet from the pivot point, so it makes sense that this would be a perfectly balanced seesaw. Force and distance of this side is equal to the force and distance on that side, okay? But what if before we look over here where we've moved the fulcrum, what if this was a much smaller person, okay? And their force was much less. Let's say they only weighed 20 newtons, okay? Man, it's really hard to write on this screen. Okay, you can see that they would be much lighter. Their torque would be much less, okay? So this side of the seesaw would go down and this side of the seesaw would go up. So if you have objects of different weights, you can start playing with the distance from the pivot point to balance it back out. And that's what's happened over here. So I have a 40-pound, it is easily referred to it as newtons, person, and a 160-pound person, okay? The distance had to be much shorter on this side than on this side to come up with the same amounts, okay? So if I do force times distance, for the little person, we've got 40 times 16. If I do the force times the distance on this side, what would that be? Where's my calculator? I should have calculated that out. Let's see. That would give us 640 on each side, and we don't really label it. It's not joules, but it'd still just be referred to as newtons times meters, okay? we really don't worry about labeling it because it's more of a comparison formula than anything. We want to try to find that balance point. You guys are going to be working on a lab that has to do with that in class, okay? All right, there's different types of levers. We've got actually 3 different types of levers. I'll move myself out of the way here so you can see that one. I'll just go down here a little bit lower. That's fine. All right, our first class lever is what we were just talking about. A seesaw is a first class lever. The fulcrum is in the middle. The input force is on one side and the output force is on the other, okay? Other examples of first class levers are crowbars and scissors, okay? So scissors are actually 2 levers, okay? My input force pushes down here. Here's the fulcrum, and the input force is going up. They're going in opposite directions, okay? If I do them both together, you can see the input force on the handles are both getting closer to each other, and then the opposite sides are doing the same. So this would be the fulcrum, okay? I don't have a crowbar, but I do have a paint can, okay? Oftentimes we use a screwdriver to open a paint can, and the screwdriver rests right on the edge of the paint can here, so that's considered the fulcrum, okay? My input force is going to push down, okay, down on the screwdriver. My output force is going to push up on the lid of the paint can, okay? The longer this moment arm, okay, the longer the distance, the more torque I'm going to get, the easier this is going to be. So if I try to open this paint can, I had a penny here. Where'd my penny go? I'll get another one. Okay, if I try to open this paint can with a penny, which is very short, a very small moment arm, it's going to be much more difficult than using a screwdriver. Okay, so it's still going to act as a lever. It's still going to have the fulcrum as the edge of the can. But I try to open it, I can't do it. It's actually starting to bend my penny. Okay, this has a much larger moment arm, and boom, it starts pulling it up. I have to move it a couple of different places, and then my paint can is open. Okay, that's how a crowbar works. If I put something on this to make it even longer, it would be even easier. Okay, so that's our most common type of lever. We also have a second class lever, and now the fulcrum is over on the end. And my input force and my output force are moving in the same direction. So a wheelbarrow is the same idea. This would be the kind of lever, I don't know if you've ever seen on like TV shows or cartoons, like if there's a really big rock and they stick a pole or something under it and they start prying it up, that would be considered a second class lever as well. And then third class, fulcrum is still over in the end, but the output force and the input force change sides, okay? So tweezers are an example of that, okay? I should have grabbed some tweezers. You pinch the tweezers and you see the output force down on the end, okay? So if these are my tweezers, I would squeeze right here, okay? And they would come together over there. Your arm acts the same way, okay? Your elbow would be the fulcrum. The muscle is going to be the input force. It's going to raise your arm, your lower arm. So the output force would be that lower part of the arm right there, okay? All right, moving on to another kind of simple machine. We've got wheel and axle, and those are all different examples of wheels and axles, okay? By definition, a wheel, an axle is just a wheel of some kind of circular object with a fixed rod going through it, okay? And they both turn about an axis point. So a screwdriver is actually a wheel and axle. The handle would be considered the wheel, and the screwdriver part would be considered the axle. When I turn the screwdriver, both parts turn in the same direction, okay? Actual wheels on a car or a bike are an example. And anything with a crank handle, anything that you have to turn a crank for, would be utilizing a wheel and handle. Doorknobs are, wheel and axle. Doorknobs are another example of a wheel and axle. Gears aren't a simple machine by themselves, but they're kind of a fancy type of wheel and axle. They are usually, attached to something right at the center part of the gear. and they just work to kind of transfer the movement to other parts. The teeth of the gears interlock and one gear will move another gear, okay? On bikes, we use gears to make it easier to climb up a hill. When you go down to like first gear on a multi-geared bike, what you're doing is you're actually using the largest gear. And if you pay attention, you have to actually pedal much more. So you're kind of spreading the force over a greater distance, and it feels easier to pedal, but you're actually pedaling more frequently to get up the hill. If you go to a higher gear, you've got a much smaller gear, so the force isn't applied over a greater distance. It's much harder to turn the wheels. You have to put a whole bunch of force into it, but you're going to move a farther distance than using the lower gear, okay? Kind of an extension of the wheel and axle is a pulley. This is a pulley, okay? So we've got a wheel and it's on an axis, but there's a groove in it. And so the groove allows us to put ropes or cables or cords or something through it. And what pulleys do simply is they can change the direction of the force. If you've ever opened mini blinds or raised a flag up a flagpole, since the flag is way up high, I've got to have a rope that goes up to the top of this pulley and then comes back down. And I'm able to pull down on the rope, down on the ground, and that actually raises the flag, okay? That only has a mechanical advantage of one. The input and the output are the same with that. But we can use these pulley systems. I can put a whole bunch of pulleys together. You know, I can get much more complicated. I could have a pulley with 3 and 2 and connect them and have all these ropes going in between them to lift things. And it's going to make it easier to lift things. If you've ever been to the California Science Center and lifted a car, you know what I'm talking about. Or Mrs. Augustine's room, you might have been able to lift yourself in her room, okay? So a pulley system is multiple pulleys and ropes helping to lift an object, okay? This first one right here, that's just changing the direction. So I have an object that has a weight of 100 newtons. The rope goes over once, I'm pulling it. I have to pull with the same amount of force. It's still going to weigh 100 newtons. It just allows me to change directions, okay? So it does make the work easier, but the mechanical advantage is still just 1. Yeah, the mechanical advantage is equal to the number of rope segments supporting the object. So if I start making these systems with multiple pulleys, they're called block and tackle systems. You can see that there's additional rope segments actually holding the object. So here's the object here. I have 2 rope segments holding that object. So it's kind of like supporting 50 newtons each side. It kind of cuts the weight in half for me. And then my force only needs to be 50 newtons, okay? Since there's 2 rope sections supporting that object, we would have a mechanical advantage of 2, okay? This rope pulling down is not supporting the object at all. That's why it doesn't count. So this one has 3 sections supporting the object. So it's cutting it into thirds, mechanical advantage of 3. And then this one is the more complicated one. It's got 4 segments supporting it. So it's cutting it into fourths. I would only have to pull with 25 newtons. And that would have a mechanical advantage of 4. This is why you have to pull the rope a lot longer, much greater distance, okay? But you're able to do it. That's why you can go and pull a rope and lift it's a Toyota Tacoma, actually, at this California Science Center. Yeah, anyway, I lost my train of thought. Or yourself in Mrs. Augustine's room, like I said. A single pulley, once again, just a mechanical advantage of 1, okay? All right.